that's given to us, I might as well put it here. All right, let's get this thing rock and rolling. Can you split this up? How about big T's on left, little T's on the right? Can you do it? 2 minus 20 equals KT. Okay. Ready to integrate? What's the integral of 1 over big T minus 20 dt? I wanted to write it like that so you recognize it is another natural log. I don't need a u sub, do I? And what's the integral of kdt? kt plus constant. This is just natural log. T minus 20. And I hope you realize it's not, doesn't this look like the last problem? Excellent. That's why I like to do these. You know, last one, Julie, was the electric circuit. Here we are dealing with Newton's law of cooling. I'm getting something, it's similar. Now E that, e to the ln of T minus 20. I know some of you probably at this point can do 2 steps at once. That's okay. E to kt plus c. So this is just what? T minus 20. I'll take the bars off because of the constant. Okay, I can just write this C, E to the KT. So there's that constant C. So we got 2 unknowns in this problem, the big C and that little k, but this information right here is going to help us to find both of those. We'll go in and figure out what they are. So what's T? Well, according to Newton's law of cooling, T equals big C, E to the KT, plus a 20. There's that room temperature. Right? Hey, if this was in Fahrenheit and you stuck this in a refrigerator and the temperature in the refrigerator is 38 degrees, right? Plus 38. That's the temperature of the surrounding environment. Isn't that cool? All right. Let's start with this. This here should help us find big C. Can we find big C? What is big constant C? So they told us the coffee was 95 degrees Celsius placed in the room. That means that T equals 0. Someone got that? When it was placed in the room, it first got brought out into the room, it was 95 degrees. Time equals 0. And the surrounding was 20 degrees Celsius, what we have here. So this number is what? 95. So this is what's happening when T equals 0. When T equals 0, 95 equals C times E to the 0 plus 20. We should be able to get C. What's C? 75. Andrew. Zona go there? So I do want to point out when this was mentioned that the coffee was 95 degrees Celsius placed in the room, we're saying time equals 0. It first hit that surrounding environment temperature and just kind of sat there. So I'm getting constant equal to 75. Well, let me rewrite this. What do we now have? T equals 75 e to the kt plus a 20. Now can you help me find k? I got this from the book, so we got to figure out where to plug this. He said, suppose coffee cools at a rate of 1 degree Celsius per minute when the temperature is 70. This is going to allow us to get the constant k. Well, that's a rate. That's not a rate, right? Just go back a few steps. Where did we have a rate? Keep backing up, back up, back up. Right here. Right here, everyone. Right here. Let me put a box on this. This is when we had the rate written. Isn't that a rate? I'm just going to make a note. Look, they said at a rate of. That right there is a rate. Let's use that portion of our work. That's why it's good to show work. And we'll use that portion of our work to figure out what the constant K is. I know, they could have given us what? They could have given us the temperature like 30 minutes later or something. But they didn't. This is what they gave out of the book. And I was like, well, let's see what we'll have to do. We'll plug it in there. This is going to allow us to find K. Let's find K. What would this be? What's the rate of change of the temperature? 1 degree Celsius per minute. Ooh, but it's cooling. Positive or negative?
Negative.
That one, they said coffee cools, gets colder, right? Hot and cold, it's dropping. It's dropping in temperature. 95, approaching at 20. I'm going to put a negative 1 degree Celsius per minute. Equals, don't know K. This is just to find a K. And then, what was the temperature when this happened? 70, they said. Look, they said this is happening when the temperature was 70. And this is going to give us the K. What's 70 minus 20?
50.
So negative 1 equals K times 50. K is just,
Negative 150.
let me get the problem. I'm just going to plug it in now, everyone. Take this, put it right into that old constant right here. And here's the final answer. Temperature equals 75. E to the negative 150. Yeah, we knew this was going to be a negative exponent. With the temperature decreasing. Negative 150 times a T.
Plus 20.
Plus 20. And this models the temperature of that coffee in that room. Hey, what does a picture of this graph look like? I just like to draw pictures. You know me. This is T. This is big T. What was the first temperature just brought in the room? When it was really hot.
95?
Yeah, it was 95. Just got it from Starbucks. 95 degrees Celsius. But then it just kept cooling and cooling and cooling. But what was it approaching? This one. So I'm going to do, here comes my whore ass. I want the 20 degrees Celsius. That's what's happening. It's just going to keep approaching that. That's what the graph will look like. There you go. That's what's happening. Newton's law of cooling. That cool. So once again, separate equations. My main reason for doing that, I want you to see the connection. Like this is just like that last problem where you end up ln on both sides. We don't always do that for when we eat both sides, because my warm-up problem, the first one, we had to L on both sides, right? So it all depends. Somebody go with that? Hey, cool. We're now going to talk about models for population growth. It's going to be very similar. They're going to give us, there's two main models we look at when it comes to 9.4. The first one you've seen before, but I'll still write it on the board. Oh, can I erase?
I have a quick question.
Oh, go ahead, Jessica.
Why is 75 turned into 70 when you're looking for K?
All right, so right here, I want to point out that this math was done right here just to help us find a constant K. We could have done that earlier. It was previous to when we found that 75. 75 turned out to be the C value. This 70 was the temperature we used from the given information here.
There it is.
But I know it's so close to that 75 we found, which was just a constant.
Thank you.
You're welcome. Can I erase? Hey, cool. All right, I'll write this on the board. You're going to be familiar with this one. What is this? Models for population growth, huh? You know, like bacteria in a petri dish. Does that work? Well, let's see what they write. I want to assume that Y of T is the population of bacteria in a petri dish. Okay, assume that Y of T is the population of bacteria in a petri dish. I do want to point out we've just entered section 9.4, but it's going to seem like you're still doing something from 9.3. All right, but assume that Y of T is a population of bacteria in a petri dish. Period. Time is in hours. Go with time T. That's in hours. It satisfies the differential equation, dy dt equals 0.044y, and they do give an initial value. At time t in hours, it satisfies that, and the initial value for y at t equal to 0, y of 0 is equal to 100. And of course, you know what they want you to do. They want you to solve for y. But then afterwards, they want you to extend the question. They go, after you solve for y, can you determine how long it takes for the population of the bacteria to triple? So, when you solve for y, that means get that explicit equation of y that models the population of bacteria. And then after you do that, determine the time it takes, and that'll be in hours, for the population to triple. Okay. Well, it's all about that. And doing separable equations, right? You ready to roll with that one? What's that turn into? dy dt equals 0.044y. Help me get that to a y. Can you separate it? Do you want to leave the 0.044 up on the right? I do. You've noticed I like to leave the constants up on the right side. So I'll just divide that what?
dy over y equals 0.044 times dt.
Armando, perfect. I think a lot of you saw this in our last lesson. You probably know where this thing's going. This is very similar to the last two problems. What's the integral of that?
Natural log of y.
L into y. Remember, if you can do two steps at once, I'm putting the integral symbol down. That's okay. That's natural log of y. That's just 0.044 t plus constant. E both sides. Guess what we did in the last two problems? ET on a y is 1. E to the 0.044 t plus c. I should write it though still. People are copying the notes. I want them to know they see this. So E to the on the y equals E to the 0.044 t plus a little constant. Well, what's that turn into?
C times e is equal to 0.044 t.
Cool. Very good.
On the test, how many steps are we allowed?
Oh, you could skip. I'm being honest, you could have gone from here to here in one step.
Okay.
I wouldn't be sitting there
That was
going,
my question, if we can see it, can we just?
Dave, was he looking on someone's paper? No, because you've seen this before, and that's good. That's really good, that you knew that this was turning into this common what? The pre-calculus equation we saw so often in a pre-calculus course, where the rate of change of y was proportional to the population of y. That's what's going on here, Ron. The rate of change of y is proportional to y, and he knew this was common. You could do it in one step or two steps. Hey, now, how do I get C? Help me get C. This should allow us to get C, right? All right, plug in 0. What's 0? That's the t, right? So I get 100 equals C times e to the 0. What's C? The initial amount. Y equals 100 e to the 0.044 t. It's interesting. You might say or ask, is C always the initial amount in every problem we do in this course? Not necessarily. That didn't happen with Newton's law of cooling. Remember we got C equal to 75? So, but in this problem it is. It turned out to be just the initial amount. All right, now it's pre-calculus time. And when you got the model, this is your model. This model's the bacteria, right? So you done the first part of the problem, but then they go, can you determine the time it takes for the population to triple? Now we're doing pre-calculus stuff. Remember how to do this? What's triple mean? What's triple 100?
300.
I'll put 300 there, keep this 100, then we'll solve for the, but the rest is pre-calculus, meaning we've done all the calculus. So I'm gonna put this in here. 300 equals the 100. E to the 0.044t. Students may ask, where do you get the 300 from? They said, during the time it takes the population to triple. That was the initial population, 100, so I tripled it. Now, help me out. We're gonna do a couple of these today.
So do you triple the C value, or do you triple like given initial value?
Good question. In this problem, it just so happens, and it happens every time with these.
Right.
The C was the initial amount, so I can say you can triple either one you want, meaning you or C, you can triple that. But the key is you want to triple that population that's here.
Okay. Thank you.
You're welcome. I just want to be careful. I know it's like Newton's law of cooling. If they said something about when did the temperature decrease by 3 times the amount, okay, we'd be careful of that. You'd look at the number they gave you.
Thank you.
You're welcome. How do you solve it? I know a lot of you are great at this. And this is where a lot of you, Dave, you included, may skip 5 steps doing this stuff.
Yeah.
If I'm solving for t, first you divide out 300 divided 100, which is what?
3.
You isolate the e, that's important, you gotta isolate the e.
Take the natural log.
Take the natural log of both sides. We've done this so many times, but if you haven't done it in a while, we're doing it now, right? Isolate the e. But this is all pre-calculus. Natural log both sides, this right side just turned into what?
0.044t.
Yeah, ln of e to the 0.044t is 0.044t. And last step, what's time?
ln of 3 over the top of 0.044.
So if your calculator died on a test, just leave the answer like this. Has anybody got a calculator? How long is that? This is an hour.
It's just about 25.
Roughly 25 hours?
Yeah.
Thank you. So it would take roughly 25 hours for the bacteria to triple. Enough problem. So this is what I mean by, what's the 9.4 models for population growth? This is one very common type of population growth, where the rate of change of that population is proportional to the size of the population, right? Cool. But this next problem, and not everything in this world grows like that, right? Don't some things keep increasing, but then they level off? Cool. I can draw that graph. You can see what that graph looks like. So that's the next one. That'll be our next problem. Can I raise? Cool. Not everything grows like this in terms of population growth. Here it is. There's our model. Does anybody, you know what that graph does? It just keeps doing what? It's bacteria. As you do something, and it was 100, and it just what? But not everything does this, right? Some things, think about like fish in a lake or something like that. I mean, sometimes it starts out really rapidly and grows, but then levels off. So this is our next model. We're going to look at something like that. This is another common type of population growth. Rapid increase at the beginning. You know, the movie Spider-Man came out. Oh, gotta see it. It was awesome. And everyone's going to the what? Week 1, week 2, week 3, week 4. You get down to week 20 and everyone's like, I'll just wait for that thing on Blu-ray. You follow me? And that's what's happening. This what? Rapid increase just stopped and they put it on Blu-ray.
Does Conway's model follow a similar?
Yes. Yes, it does. It does. And for this one, this model, everyone, I want to present it to you, but I would like you to help me show why it turns out to be. So what we're saying is this last one, you don't have to copy this down. This is what we had before. We just had that, and Dave, you said this turned into what? Y equals C e to the kt. Did anyone notice that? This type of population growth, we did all the separable equations, turned into that, didn't we? But I didn't show it to you. I knew you could figure it out. You did it. This next one, the work is a little more complicated. Not a big deal, but let me show you what that actual model is, and we'll put down what it is. But I want you to help me show what it is. So I'll put this down. Here we go. Okay. is another, I'll tell you what this is called. So P is for population. Kp times 1 minus P over M. And when this is a logistic differential equation. Now you know why I signed that one problem in section 9.1 when I was like, can you tell me when the population was increasing and decreasing? Do you remember that problem? It's something very similar to this. We can figure out at some point the dPdt actually can become negative and stuff with this type of relationship. So this is a logistic differential equation. Can you help me show that the solution for this, that model this, I'll just put the model, is P equal to M over 1 plus AE to the negative KT, where A equals M minus initial P over initial P. Those P naughts, everyone that I wrote, are just initial populations. Alright, so we're just going to leave this up here. But I'd like you to help me show that, and then we'll work a problem. Once we show that this is true for logistic growth, this type of graph, again, everyone, if you want to see a picture of this P, what it would look like when you plug in a bunch of numbers. We're talking about something that might do something like that. Logistic growth. Increases fast at the beginning. It kind of levels off. All right, first I got to talk about some of these letters. We know K is an unknown constant, right? P is the population they're talking about. This M, that's called the maximum capacity, or the carrying capacity. So M is the carrying capacity, right? Some environments just have a certain population that it just can't go over, right? That's that carrying capacity. Whatever environment it is, the population's not going to exceed this population size, which is what you saw with this. There's that M value, right? So that's what M is, everyone. M is the carrying capacity. I just want to make that. The carrying capacity. But rather than just give you the equation, we shouldn't. Here's an equation, deal with it. Can you help me figure out why this turns into this? See, before, what did this turn into? dy dt equal to ky turned into y equal to ce to kt. Can you show me that this logistic differential equation turns into this? Right? It's going to take more work than this, though, isn't it? But we'll get it. We'll get it. All right. Then we'll put some values, and then when we're done, we'll get what's the carrying capacity, get some numbers, we'll solve the problem. Sound cool? All right. First thing is, here, this won't take long. Everyone, can we separate P's on the left? I get dP over P times 1 minus P over M equals, what's on the right? KDT? We're trying to get to this thing. But we'll get there. Here's my first suggestion. Do you all notice I have a complex fraction? I don't like complex fractions. I recommend right now, could you help me multiply M over M over here? Help me, let's just multiply M over M to this expression right here. Because I don't like this complex fraction. See the P times the 1 over P minus M in the denominator? They call that a complex fraction. So I'm going to multiply M over M to this expression. Well, what do you get? What's this turn into?
P over M.
And I'm writing a little smaller, everyone. Let me know if you can't read this, because I know this is going to take more steps than the last problem. I'm like, all right, I wanna make sure I got enough room here. I think I do. But if you can't read something, I'll make it larger. If I do this, now what do you have? You got M over P times, I'll just put the M in here, and then M minus P, right? Hey, cool. So how in the world am I going to integrate that left side? I'm ready to integral. I'm ready to do the integral of this. I'm ready to integrate. I want you to think of those p's as x's. Who recalls in our course, how do you deal with something like this? I'm going to give you an example. You got it. So that's what we got to do with this. This is why I wanted to say, hey, can you help me show to get here? Do you realize something? We got to do partial fractions on that left side, right? Very good eye. Do you see it? It's like that. That p is the variable. This m is just a constant. Well, don't let the m bug you. That m is just like a 2 or 5 or 100 or 20,000 or something. So now, let's do this with partial fractions. You know, with partial fractions, we do 90% of the math without doing an integral, right? So let me get this set up. Now here comes my partial fractions worth. All right, let's get this thing broken up to partial fractions. M over p times m minus p equals, don't use the letters a and b. A over p plus b over m minus. Okay. We multiply m minus p, we multiply p, right? M over p times m minus p equals a times m minus p plus b times p. And I think now we're ready to roll. I'll get out of the way when I want to see this. Again, Dave, if you can do like 2 steps at once, that's fine. And when we're just trying to figure out a and b, boy, there's a lot of constants in there, aren't there? That's what I mean. Again, I want you to show this problem is not as light as the last one. All right, so remember what we did? We concentrated on the top. Let's just focus on that top. What do I have? M equals A times M minus P plus BP. All right, we got to find A and B. Connor, you okay? We do the shortcut thing, the if stuff, like we did before. Remember with the partial fractions? We go if this. That's what I'm going to do. So when P is your variable like that. P is your variable like that. So ready? Here I go. If P equals M, could you tell me what you get? We should be able to figure out one of the letters. If P equals M, what happens? We get P equals A times, what's this turn into? 0 plus BP. What's P? We just found one of the letters. What would B equal? P equals 1. We just found one of the letters. If P equals M, P times A times 0 plus BP, P equals 1. Now I hope A is just as simple. Let's try that. I'm going to use this one. Everyone, here we go. What if P equals 0? What do you get? This is the hardest part to the problem, just dealing with partial fractions. I let P equals M, I got B equals 1. What if P equals 0?
A times
All right.
M equals M.
M equals A times M plus a 0. So what's that?
A equals 1.
A equals 1. We got him. You're a happy face. We finished partial fractions. We figured out the A and B. They came out so nice. A is 1 and B is 1. Well, we did a whole roll here, so we're halfway done. We're halfway done, everyone, but we'll get this. We're getting closer to this. We just had to do the antiderivative. That was not an easy antiderivative. We just did partial fractions. Okay, here I go. Now I will find the integral. So I'm going to come back to this. What is this equal? And the integral of this M over P times M minus P. And this has a dP in it. I apologize. I'm going to put that right here. Yeah, dP. A dP equals the integral of k dt this just becomes kt plus c, but let's, before I do that integral, let me just replace this. This is the integral of 1 over p plus
M minus
1 over m minus p dt. Make sure it's a capital P. But that's going to be easy now. Look at this. So when we get the partial fractions. Isn't that cool? That m in the top got thrown out somehow? This looked weird before, didn't it? Again, why I wanted to show this. I wanted you to show how to get this. All right, what's the integral of this? There's something tricky in here, everyone. Oh yeah, that's easy. That's not. Who knows that antiderivative? It's a natural log. It's a plus or minus. It requires a u sub. Good eye. That's why I want to make sure, and another reason I wanted to show this with you. Boy, this could tie you up. Is that just the ln of m minus p? Wait, p is the variable, right? What's in front of the variable?
Negative.
So by a u sub, this becomes negative natural log of m minus p. But that's by a u sub. So I just want to, maybe I'll highlight in yellow. That was by a u sub. If you wanted to go off to the side and say let u equal m minus p, you would have got the du equals the negative dp, and negative du equals dp. That's what you would have saw. And you would have saw that that's actually negative. But I hope everyone realized you're like, okay, I don't have to show all that work. I know this will just become negative natural log of that by the u sub. See the negative right there? That's why it's, but I want to put this off to the side in case you're curious. So feel free to put that in your notes. Why is this becoming minus? There's a negative in front of that p. Every other problem I did today was like just a +1 as the coefficient to the variable. Before we did these natural logs, Julie. This is the first time I got a little minus in front of the variable. That's what would happen by u sub. But hey, if this was minus 3p, I would have had a negative 1/3. All right, what's the right size integral? That's easy. All right, we're getting there. We're getting there. How do you write this? I don't keep the bars. She goes p over m and p with the natural log. Sean, excellent. Everyone right? By log properties, I can do that. So now, if I e this and I e this, what do I get? E to this, what's this? E to the kt plus c? But no, this is where I want you to study something. I want to get this, right? We're closing in on this. We're so close, but this has what in front of that k? I notice the model has a negative. I would like right now, if you don't mind, can we just force a negative on in front of that k? How would I do that? I just have to multiply a negative on both sides.